Hi, hello.
Hello.
Yeah.
Let's begin.
Yes, please.
Thank you. Good day, everyone. My name is Heroes. This is our work on resolving atomic structures of altermagnetic material, NT, by scanning tunneling microscopy. So, what is altermagnet? It combines the features of ferromagnet and anti-ferromagnet. Zero net magnetization, but giant band splitting. NT is a well-known altermagnet whose spin structures has been resolved by RS, and the band splitting is about 0.8 electron volts. In addition, NT has a high near temperatures, around 307 Kelvin. Below these temperatures, it keeps long-range spin orders, forming the altermagnetic phase. And we use scanning tunneling microscopy and scanning tunneling spectroscopy to study NT. And STN shows topographies, and STS shows electronic structures. Now, let's move on to bulk NT. We first cleave bulk NT under ultra-high vacuum at 77 Kelvin. And here is the STN topography results for the cleave bulk NT. Well, it shows the two distinct surface faces, one showing a typical hexagonal lattice with dark and bright defect, and the other showing a Kagome-like superstructure. Here is the Kagome shape. This is the Kagome shape, and their lattice constants is around 440 picosecond, perfectly match the literature scale. And this is the first time that Kagome-like superstructures be reported. And now, let's move on to the STS results. Well, you can see that the two surface faces show the similar spectrum, but we can notice that an extra peak split near the boundary of the Kagome phase. Okay, now move on to the thin film NT. Well, thin film NT is also an interesting problem for low dimensional magnetism. And we try to grow thin films in our labs. We first cleave Bi2T3 substrates under ultra-high vacuum. Then we deposit NN on the Bi2T3 substrate. And finally, we transfer the samples into STN for imaging. And here is the STN topography results for after we depositing. Well, there has shows a small NT islands formed on the Bi2T3 surface, and the apparent height of the islands is 528 picosecond. And this island shows one by one hexagonal structures, indicating that NN and T are starting to assemble and on the substrates, but the surface remains rough. So we will try co-deposition of NN and T to improve uniformity. And to summarize, we successfully cleaved and scanned bulk NT and revealing two distinct surface faces. Their lattice constant is around 440 picosecond, perfectly match the literature scale. And for the thin film NT grown up the Bi2T3 substrate, well, the NT island formed by the NN depositions, but the surface remains rough. So we will try co-deposition of NN and T to improve uniformity. And our next step is to try spin polarized STM to reveal MT magnetic structures at the atomic scale. Thank you.
Right. So my question is, can everyone do it? I mean, where is your personal touch? I mean, you have a big machine, you have a powerful machine. Do you just go with a team? Everyone can do that? I mean, where is your ingenuity here? Engineering. Yeah. I mean, you have a machine. I mean, everyone can do it.
Yeah.
Is that true? So, what's special about your personal contribution?
For example, well, all of the of the works I had do, but it's like a work with another team partners in the lab. So, for example, for STM, we need to have 2 people to use the machine, so we can scan the topographies. Yes, and for the data measures.
So let me put it this way: can robot replace you?
Robot?
Yeah, replace your
What is replace?
can do it automatic. I mean, if there's no personal touch,
Oh yes,
we can put everything to automatic. We don't need.
For the final part, when we transfer the samples into STM chambers, and then we can use the machine to scan the topography, the height, and the detail of the yes.
Why this study?
The study is important because NTE is a well-known altermagnet. Altermagnet combines the features of ferromagnets and zero anti-ferromagnets, and it got the features of ferromagnets is giant band splitting. Here is the our best results for the giant band splitting. And why we say giant band splitting, these features is important. It's because when we, for example, when we use a current through the NMT material, and then the current will be polarized. And let me explain what is polarized. Because electron has the spin up and spin down states, it's the generals for the states of the electron, spin up, spin down. And for polarized, it means that the ordinary current is only combines the current spin up and spin down current. They are combined together. But when we through the NNT materials,
Right. Good.
All right, thank you.